Thank you, Douglas, for the intro. I'm audible, right? So I'm Anoop. I'm a GTM specialist for model training and inference on AWS. Typically work with the customers who are using AWS infrastructure to do large-scale training, post-training, or inference. Kunal, do you want?
Yeah. Thanks, Anoop. Hey, folks. I'm Kunal Jha. I'm a product manager on AWS AI platforms. I look at customers looking to, as Anoop was saying, pre-train, post-train, deploy models on AWS compute platforms, specifically SageMaker AI. And today, we are going to talk about how customers are utilizing that compute platform for a lot of their key use cases, and what infrastructure benefits and application benefits, and how do we tie that in with Ray.
Yeah, I think you cannot hear.
Am I not audible?
Yeah.
Oh, OK. Maybe I'll just try and speak louder. Maybe
yeah,
this is
speak
better.
louder.
Yeah.
It's a small room, so.
Yeah.
Yeah. OK, sorry. I didn't do that. These will be recorded.
Yeah, then it might better to get a microphone.
Can we switch on the microphone?
Yeah, they're on.
They're already? OK.
I guess we'll just roll with it.
Yeah, let's start. I think we are 2 minutes over. So yeah, so the topic of today's session is how to scale up your post-training workloads, and specifically what are the things that we can do at the workload, at the infrastructure level, at the workload level, and at the orchestrator level that helps you scale it up across thousands, or now we are seeing tens of thousands of GPUs for post-training. Before I do that, why are we here? Right? Why are we talking about it? So if you guys remember, when we started 2025, everybody was saying this will be the year of agents, right? The year of agents 25. Still, we are there. We have some agents in the market already. But if I have to do at the end of the, almost at the end of the year, it's the year of capabilities, right? Where your models are becoming more and more capable on doing very specific things, like solving maths Olympiad for a problem, for example, doing physics Olympiad, doing completely new things that we thought not even possible earlier, especially on science and other aspects. And the way a lot of the customers achieved those capabilities is by scaling up post-training. And in particular, scaling up post-training using reinforcement learning on this. You saw the same theme. I think I looked at the sessions for this Ray Summit. There are probably at least 15 sessions just on the topic of post-training. And that would give you some of the innovations that are going on in this domain. I clearly separate out pre-training versus post-training. Pre-training is where you have jump a bunch of data, you put a lot of compute, you have a base model ready. Post-training is more of an art, where you have to figure out what is the data set, what are the different ways I should post-train, how do you optimize it for your use cases or for the desired behavior. But more important than that, typically what we see is how do you use it use the compute more effectively to build the model as quickly as possible. But we are at the Ray Summit, and what are the most common things that I see? There are multiple post-training frameworks right now that has combined pre-training, both the training and inference architecture. Almost all of them are based on Ray. There are some that are not, but most of them, the popular ones like Verl or SkyRL, NemoRL, they're all built on top of Ray, where Ray is the compute engine for this. And Ray is essentially the orchestrator that is distributing the workloads across your compute or networking and storage workload. We see that quite often, but typically the concerns or the challenges that we see from the customers is we talk about heterogeneity of the clusters. So it's not a bunch of Hopper or Blackwell GPUs that is crunching your data, but you have a mix of different types of GPU types, different way of getting those GPU types, and a lot of CPU instances as well. So how do you optimize it for a heterogeneous cluster? I think the industry has not probably nearly settled on this, but most of the models that we are seeing on the post-training are the large MOE models, a mixture of expert models. And the way it brings up complexity or benefits is now you have a model that is very large, but that can be distributed, and there are new ways of parallelism that you can use to optimize performance. Entropy is a big challenge. Entropy from the infrastructure, entropy from the workload, entropy on the how do you even do your rollouts, and how do you manage your data sets to optimize the rewards, that is challenge. And I think what I've seen is the small variation will give you completely different models on this. And then, as I mentioned, as I showed in the previous slide, the stack is still evolving. I don't think there is a single framework that has like a big market share, but many of the customers are building their own framework on top of it. So you need a flexibility of stack. Cycle time is important because what is the iteration time from that from that entire cycle before you can evaluate the model? And the cycle time, a part of it is what are the things that we can do to improve the iteration time? And one of it is obviously rollout performance of the rollouts, but also because there are a large number of distributed compute engines that are operating, how do you optimize it for, let's say, data transfer or model data transfer from one to another? A lot of these innovations will come from the framework or even from the workload on this. But one way to optimize it is from the infrastructure itself. Can you build an infrastructure or ML platform that gives you all of these capabilities by default in it? And that's what we are talking about today. Why we need it? I talked about challenges earlier. But if you don't have an optimized infrastructure, even if you throw a lot of compute, you will have inefficient rollouts. You will have slower training cycles. You have longer iterations. And essentially, if the iterations time is longer, it results in higher cost and probably missing market opportunities on this. And this is something common I heard from customers after customers after customers on this challenge. What can you do on the infra side to optimize it? So a couple of years ago, we released an infrastructure AI platform that is optimized for model training and inference, which is SageMaker Hyperpod. The goal of SageMaker Hyperpod is to improve the efficiency of your compute platform so that you can reduce the time to train, for example. Primarily, it was built for optimization of pre-training because pre-training was dominant workload a couple of years ago. But the same innovations that we used to optimize it for pre-training, we're finding is even more useful or more beneficial for scaling up your post-training workloads on this. The goal is very simple. How do you get to the best model at minimum cost? And it means that how do you get to the best model with the highest utilization of the GPU, or what we call as the highest goodput from your GPU cluster, depending on whatever the AI workloads you are running. The core components of Hyperpod is resiliency, versatility, and efficiency on this. What does resiliency mean? GPUs are, I would not say susceptible to failure, but yeah, they do fail a lot. And when they fail, it can fail for different reasons, and it can manifest in very different ways. Sometimes a issue that you might be debugging into your model convergence might be because of a hardware silent data corruption. Right? That wastes a lot of cycles on the engineering time. That wastes a lot of cycles on the compute time. And every failure is a challenge there. What Hyperpod does is take that complete equation of GPU failure, okay, the problem, take it out of the equation completely. So it proactively detects, before adding any new node to your cluster, proactively detects if there are any hardware issues into that node. More important than that, it has some monitoring agents that are running on every node during your run to figure out if there are any hardware issues that might occur during the operation. And the number one thing that it does is, if it detects a hardware issue, it stops that instance, it gets the instance from a spare capacity, spare pool, and automatically resumes your training from the last saved checkpoint. It's completely making your workload resilient and failure-proof on that. But by doing that, we saw the training time getting reduced by more than 40%. I talked about resiliency, but more important than the versatility is more important. Because as I said, right, you cannot have an opinionated platform when the industry is moving so fast that you have so many new frameworks coming up very rapidly and gaining adoption. So think of Hyperpod as the bottom 2 layers that are managed, the compute, storage, and networking, and the AMI is managed. Everything else, you can use whatever you want. You can use a array on top of it. You can use any framework for serving, VLLM, SGLang for serving. You can use PyTorch, or you can use any distributed training framework. And on top of that, you can have a CI/CD pipelines or a job submission platform on that. I'll come back, but if you want to, let's say Hyperpod, think of Hyperpod as just a cluster that is optimized for AI/ML training, which can be accessed through a Kubernetes control plane on this. And if you want to run array workloads on it, we do it through kubearray operator. Because you have access to those instances, you can SSH to those instances, you can install the kubearray operator, and then you can create these array clusters with different array head nodes and the worker nodes, and you can have different clusters, heterogeneous clusters to run your workloads. I'll come back, but before we do that, there are a couple of features that we would like to talk about that optimizes the post-training.
Thanks, Anoop. And so as we were seeing before, that the customer interaction with Hyperpod in case of array is happening through either kubectl or AWS Array. And within the Hyperpod control plane, the kubearray operator and the nodes are kind of interacting within the control plane with respect to orchestrating and managing the resources. Now, as Anoop was talking about how there have been the key challenges that customers face when they're running any massive workloads are always with resiliency of those workloads. What can they do to maximize their usage of GPUs? If the few things that Anoop talked about with respect to how Hyperpod helps with both ensuring the nodes are all checked, deep health checks are on a node before they're added, so their chance of failure is reduced, how it continuously monitors and automatically replaces those nodes. And even in case of resiliency that is offered, there are further efficiencies that customers can get. In terms of overhead that we see with respect to the customer usage, there are around 10% of overheads that come from just checkpointing with respect to how fast you checkpoint, since it's a sync operation, and once failure happen, how quickly can you load from there? And so one capability that we launched recently was we provide a disaggregated memory store within SageMaker Hyperpod that helps you with all of these checkpointing needs. You can make use of that disaggregated memory store to take checkpoints as part of sync operation where offload from GPU to CPU memory happens and your job restarts, while behind the scenes, that capability, which is managed tier checkpointing, takes care of replicating these shards across different nodes to offer you higher resiliency, and also storing that to a durable store every few so often if there's catastrophic failures that happen. And so primarily how it helps customers is they can checkpoint more frequently because checkpoint save times are 2 to 3x faster. And they don't need to take care of the replication across nodes. That is automatically taken care of. If failures do happen across, let's say, one node or two nodes, the checkpoint, the model loading happens directly from memory with respect to another checkpoint shard that is saved on or replicated on another node. So customers see up to 4 to 5x increases in their model loading time, 2 to 3x better model saving times. And so they can checkpoint more frequently. And when they do lose a node or so in between, they don't lose a lot of progress because they're checkpointing more frequently. So this helps reduce the overall checkpointing overhead that you see as part of any training processes. The other part that we worked on in a large-scale cluster is how can we kind of cut down on this overhead, both with respect to checkpoint and process overheads. Primarily, until a node failure is resolved, training is not resumed. So there's a lot of GPU hours that you're kind of losing all across. And so for example, in a very large-scale clusters, and we have run this on clusters with like sizes of around 15,000 GPUs and higher. And you see across the span of a day, there are multiple times where you're seeing fault across. And so primarily, customers want to quicken the time to which their overall training job or time is down. And so primarily, process level restarts takes care of that 7.5% of process overheads that we see. With respect to total, like 10% from checkpointing, 7.5% from this, around 15 to 17% of overheads that we see as part of an overall goodput that you want to get. And so primarily, it keeps the pods or containers alive while surgically looking at the minimal unit of failure, which is the process, which is restarted. So what happens is when you're actively doing a restart, that restart happens pretty quickly, and your training can resume faster. Apart from that, as we see customers scale across the different parts of model development lifecycle, they started with pre-training. They have started kind of doing post-training. They've also started looking at utilizing the same compute platform to deploy their model also that have come from their training, post-training, from the pre-training and post-training. So on the infrastructure layer, we are doing a bunch of key improvements to cut down the time it takes for nodes to get provisioned. You, as a customer, just have to submit the state that you want to be in with respect to how many nodes you require, what capacity you require. And Hyperpod on its side takes care of provisioning of the infrastructure, continues to retry if there is no availability, so that customer doesn't have to manually try to sync their need with what the state of the system is. And beyond that, if there are flexibility in your, if there are changes in your traffic patterns, you want to ensure that your pod autoscaler is also backed by a node autoscaler. And so primarily, we have also integrated Carpenter, which primarily customers use for node autoscaling, as a managed Carpenter offering within SageMaker Hyperpod, which can scale down to 0. Hyperpod takes care of management, installation, operations, et cetera. Customers don't have to worry about that. And primarily, it looks for any unscheduled pods, autoscale based on the pod characteristics, autoscales, and works with Hyperpod with respect to autoscaling fast. Finally, one key aspect as part of inference is like everyone is looking to decrease the latency, increase TTFT, time to first token. And so there are a lot of new things that are happening in this space with respect to what all things you can do and how easily you can implement it as part of your deployment workloads. So as part of this, we provide customers capabilities to utilize KV cache layer that I was talking with respect to a disaggregated memory store, and plug that in easily within their deployment YAML and be able to kind of plug that into their overall inference workload. We have seen customers get significant improvements in their latency, in their time to first token, and we want to provide customers easy to use mechanism with respect to containers that already have these capabilities kind of packed in and are just good to go. And finally, Hyperpod automatically labels network topology for the nodes that it brings up, which can be then utilized by a scheduler to kind of ensure that the workloads are within a specific networking configuration, both for different kind of nodes, even for ultra clusters or GB200s. And it opens up or provides that flexibility for customers to kind of build on top of that. OK, and so based on all of this, what Anoop would want to kind of showcase, how we have created an example that is plug and play, that you can utilize for your different needs with respect to training, reinforcement learning, and kind of utilize that on SageMaker Compute Platform or SageMaker Hyperpod, And there would be a GitHub link at the bottom that can be used to kind of see, explore, and plug and play. And so Anoop, if you want to talk about that.
Thank you, Kunal. Yeah, I think we talked about the platform, right? Essentially, the platform that you can use to build or run your post-training on, right? Which provides multiple capabilities. We picked up some of the features that we found useful for post-training optimization. Most important than that, how do you even scale up your post-training, right? Assuming you have a platform that is resilient, that's fast, that's efficient, what are the ways you can not just try it out, but actually do scale it up for fine-tuning or reinforcement learning of a very large model. So this is the architecture diagram. This is available in that GitHub link. Feel free to take a look. You can download it. It will allow you to create a cluster through this. There are a couple of other things that you have to do, but feel free to get in touch with us. But it's, as I said earlier, the EKS or the Kubernetes is the control plane for everything here. And what we have here is a Kubernetes control plane which has 3 data planes. One is a hyperpod instance group. The one is plain EC2 instance group. And then we are using some spot instances from the fully managed platform, which is SageMaker Training Jobs. And this. We have observability through Prometheus and Grafana. So based on our deployments, we have some opinionated stack. We have created some opinionated dashboards that will help you not just workload observability, but also cluster observability on how it's going. What it does is if you want to do a train, you can do a heterogeneous cluster with different GPU types on this. You can decide to do training on the hyperpod, do the inference on, let's say, the spot instances, or you can do the training on inference, everything on the hyperpod instances. It's all, you feel free to use different ways to achieve it. This is, I think we are using Verl for this, for the post-training library. So just essentially a one-click install, it creates a cluster, and then you'll be able to do Verl reinforcement learning. Obviously, the size of the cluster is dependent on the size of the model that you will be post-training on, but it gives you a quick way to build a cluster that is ready-made and efficient for post-training workloads on this. For tracking or for evaluation, we use MLflow, and this the SageMaker's managed MLflow for building this. This is a quick demo. I don't think it's coming, looking. It's a little blur, but yeah. And we have a full demo in our booth as well, in the AWS booth. I talked about observability in this. Some of the key things that a lot of customers like about it is now you have a Ray dashboard, which has infrastructure metrics built in, right? Not just the ones. Ray gives a pretty good dashboard of it itself, but we have added additional things onto the infrastructure on how different teams are using this work, how different tasks are using it. What are the priorities, right? You're maybe running a post-training workload, but suddenly you need GPUs for your real-time inference. Okay. So it will show you some of those workloads, like what are the priorities of the workloads that are running on these dashboards. It's not just the compute. It's usually networking and storage that sometimes they become the bottleneck. So how do you get so single dashboards that will have everything? So essentially, in this talk, we talked about a platform that is optimized for AI/ML training, AI/ML post-training workloads, and how it can be used for especially scaling up post-training workloads by building a heterogeneous cluster, by building a resilient cluster, by building a cluster that is optimized specifically, let's say you're doing weight transfer across different workloads. And it has been deployed quite a bit across a lot of customers. And I think one of the largest customers for Hyperpod is Amazon itself, where we use it for building our Nova models on it. If you want to know more, there are a product web page and demos and the developer guide here. That's all for me. We have 5 minutes. Feel free to ask any questions on this. Yeah. Okay.
Go back to the checkpointing slide.
Yeah, sure.
The question is, because we do frequent checkpointing, these instances could be deployed in multiple availability zones within a region. Is the cost all inclusive, including network, when we do checkpointing, like when it gets replicated on the instances?
So I think typically in a lot of scenarios where there's a large cluster size, typically we see customers keep it within a specific availability zone because it is a sync operation. And since it's a sync operation, you want to minimize the time in which their networking hops, etc., kind of happening. And so typically it's kept as part of the overall same availability zone. But with respect to hypothetically, let's say if you want to have this across different availability zones, etc., I think there's no additional networking cost that you're charging here. Or maybe
So I think it depends on how the agreement with AWS is. So yeah, there will be a separate charge for the compute, there will be a separate charge for networking, especially cross AZ networking or the data transfer on this. Because typically, usually when we do hyperpod, essentially it's just the compute nodes that we not just try to keep on the same AZ, but also on the same spine, because data transfer is expensive, yeah. But I think if it is cross AZ, you will see a network charge. I don't recommend cross AZ even for post training. So I would recommend same AZ. Yeah.
So I have 3 questions if you don't mind.
Okay.
Introduction. So for this slides, those instant CPU, like instant Q to instant N, those are standalone CPUs in the source as part of the training parts as well.
sorry, there's.
So those like CPU instance, like instant Q to instant N.
No, so primarily I think all of these are GPU instances whose CPU memory is underutilized or their NVMEs are underutilized. And so primarily what happens is there is an offload that is happening across every node from GPU memory to CPU memory. And then the training starts up again. And then behind the scenes as an async operation, the replication is happening across different CPU memory across these nodes.
So those are just duplicate, like redundancy, right?
Yes. So basically when your one node goes down, let's say instance 1 goes down, its checkpoint shard is also there on instance 2 and instance 3, so you can directly load from there.
Yeah. And what if you like this have against it, you have like instance 1, 2, and local brackets. So in that case, you don't have any instance limits. So which means they have to still go back to S3.
So yeah, let's say there's a catastrophic failure that happens where you lose, I don't know, 50% of your cluster, for example. Yeah, so like if in case of if there are replicas that are there, it can load from the replicas. But let's say there are multiple there's a catastrophic failure that happens, then there's always the durable store that you can fall back to, which is S3.
So basically, like from the memory to S3 is a different schedule. Like it's not scheduled to be like few minutes.
Exactly. So it could be like earlier you were doing save to S3 every, I don't know, 100 steps or 10 steps. Now you can do save to S3s every 1,000 steps or so, because you don't need to save that often to S3.
So follow-up question. So do you have any on-demand checkpoint? For example, if I know I'm going to be connected, do you like, does this thing catch a signal, automatically do the last minute checkpointing? Do you have something like that?
Sorry, I didn't get that last part of it.
Termination signal happening. So for example, like I know there's going to be some disaster happening.
Yeah. So if you, I guess the part that you're asking, can you do this on demand?
Yeah.
That can be easily integrated in your training loop code. And you can invoke that and kind of run this part of the process.
And last question, what is the interface for this? It's like majority of people do checkpointing, they write to S3 or write to a local location. What's the interface?
So primarily the integrations are using PyTorch DCP. You can utilize Ray also. That's why it works perfectly well with Ray also.
I think there's a question here.
I was mostly answered by that question. I was going to ask, is there a rebuild time or is it instant? Like it's constantly checkpoint, and the minute that there is detection that instance 1 went down, one of the backup instances picks up, and is there any downtime, or like there should be some sort of health check that you're doing that'll make instance 2 pick it up? What is that downtime?
So I think there are two things here. One is when one node goes down, there is Hyperpod detects it with the health monitoring agent, and then it tries to do a reboot and in quite a few scenarios, reboot fixes that issue. And so you can pretty much get that started within minutes. But there are certain times where there's like hardware failures that happen and you want to do a replacement. And so as Anoop was saying, that there's a spare capacity pool that we maintain and the replacements happen from that spare capacity pool. Those also happen within minutes. In the case of checkpointing, once, let's say, a net new node is brought up, you have done the replacement. And so you want to load the model, and primarily the other instances that were running before have that checkpoint shard. And so for the instance one, which is replaced with another instance, its replica is there on another instance, and it's loaded from there. And so typically, we have seen significant improvements on like 4 to 5x improvements in terms of the time it takes to do all of this part of the process, because you're loading from memory, and it's happening super fast.
Yeah. And
And the new node that comes up, is that a GPU instance?
It's a GPU
It's-
instance.
exactly the same instance. Same.
Yes.
I had another question on your another slide that talks about auto scaling.
Yeah.
So out of the box, like what metrics are you using to scale up your array cluster, GPU clusters? Like, is it just CPU memory, or are you looking at some QLEDs somewhere?
Yeah, I think
this one.
we may be getting kicked out. So what I can do is we can hang around here and answer questions so that we don't exceed the time for this room. But I'll be here for the next 15 minutes or so if you have other questions, and I can kind of answer all of those. But appreciate all of you guys kind of
Thank you
coming
so
in.
much. Really appreciate it.
Really good talking.